Hello, this is Teach Nichols, and this video is on the work-energy theorem. The essential question for today is, how does energy move into or out of an open system? So this is a really big, important question because it gets to the how energy actually moves around in our universe. So compared to mass, it's much harder to keep closed systems for energy. The reason is because it's pretty easy to contain all the mass of an object in a box, and if it moves around, it's all still in the box. But energy takes so many different forms, like light and heat and sound, that to truly make a closed system for energy, you can't let any of those things escape your box. So the truth is, we're usually dealing with open systems for energy. And that means the energy of objects, the total energy of an object is changing all the time. So let's take, for example, that stroller. The energy of the stroller is primarily kinetic motion energy. There's some rotation energy and some other things, but obviously the energy of that stroller is going to change constantly as it is pushed along the street. The primary energy inputs, if you remember, we draw energy inputs as arrows going into that box representing the dashed box representing the open system, is energy from the dad who is pushing the stroller. Another way to say that energy is changing in a system is delta E. So this is the delta E from the dad. We don't care about where that energy came from in the dad, the type of energy it is, because it is entering our system, so we only care about its effect on the object in the system. There's also energy leaving that stroller system. Because it's rubbing along the ground, there is an energy output or a negative delta E from the friction of the stroller rubbing against the ground. If these are the only energy inputs and outputs, then you can know that the delta E for the stroller, the overall change in the stroller's energy, is going to be the delta E from the dad and take away the delta E from the ground. So there's actually an equation that lets us calculate delta E from any object, which is super, super useful in terms of physics because it's a general equation that you can use with lots of different kinds of energy. And there are two mathematical relationships that go into building up this equation. The question for the first one is, if you had two horses, which one would change the energy of a cart more? Now, this is pretty obvious. If you look at it, the mini horse is only going to be able to exert a small force on the cart that it's pulling. Therefore, it's likely to change the energy of the cart a little bit less. A big horse is going to exert a large force and therefore cause the energy of the cart to change a lot more. So in general, the more force an object is exerting into a system or out of a system, the more energy that system is going to gain or lose. Therefore, there is a linear relationship between a force and delta energy. The second mathematical relationship is a little bit less intuitive, and it has to do with how we physicists define energy. It turns out that in order to actually change the energy of an object, the force has to act over a distance. Just pushing on an object that's standing still isn't going to change its energy. It's still standing still. So you actually have to get that object to move in space if you want its energy to change. So 3 examples of skateboarders. Let's assume they're all able to skate well. They're all pushing on the skateboard with an equal amount of force. Well, this skater, the first one, doesn't move anywhere. They're just standing still on the skateboard. Therefore, even if she was pushing on the skateboard, which it's hard to tell if she is or is not, but in any case, we're not going to have any energy change of that skateboard because it's not moving a distance. Second skater is moving that skateboard a small distance, and so therefore the skateboard is going to change energy, but not very much because the distance it's moving is relatively small. Of course, that third skateboard ramp allows that skateboarder to push for a large distance, and then obviously that means that that skateboard is going to change energy or gain a lot more energy than the other 2 skateboards. So overall, we end up with another linear relationship between the distance of forces acting and the overall delta E for that force. So you put these 2 simple linear relationships together and you end up with something known as the work-energy theorem. And I would argue this is the most useful equation in all of physics. So get this one down and get a good box around it. Essentially, we know that delta E has a linear relationship with forces and also a linear relationship with delta D. Therefore, delta E is equal to force times distance. There's another name for this quantity, this force times distance quantity. This is sometimes called work. So you can kind of think about this as work causes an object's energy to change. Delta E is the same as work. And when you think about doing a lot of work versus a little work, exerting a lot of force on something for a lot of distance is obviously going to make more work and make that object's energy change more. Work can be positive or negative. If you have an open system with positive work, we assume that the objects in that system are gaining energy. Or sometimes you have negative work from a system. That sometimes is described as work by the object. And that will decrease the object's energy. So work can either go into systems or come out. It can be either positive or negative. So I think most professional physicists and engineers would agree that energy is actually the best and most powerful way to solve quantitative, that means mathematical physics problems. If you actually want to solve for a solution for almost any range of physics problems, understanding what's happening to the energy inputs and outputs is key. The reason it's so great is because if you can be very careful about how you define your system, then it's usually relatively easy to figure out forces going into the system. It's usually easy to measure how far that system or the objects in the system move, and that's going to tell you how much energy is going in. So for example, we can measure using a force probe how hard the dad is pushing. It's easy to measure how far the stroller moves, so we know how much energy it's going to gain from the dad. Then we can also take away some energy from the system. It's pretty easy to measure or calculate friction. It's pretty easy to measure how far the stroller moves. And so we can overall figure out the delta energy or the overall energy change from the stroller. The cool thing and crazy thing about this is that it works for all kinds of forces and energy transfers. It works for rotational forces. It works for electric forces. It works for forces in fluids and thermodynamics and all sorts of different forces that feel really unrelated to each other can all be combined and solved problems using this work energy theorem. Okay, we've reached the end of the video. Please take a minute and revisit your essential question, which is how does energy move into and out of an open system? And we will do some practice in class. Thanks for watching.